All right, today we're going to go over on how to graph quadratic functions using transformations. And we haven't even talked about what a quadratic function is. But before we get into that, I just wanted to remind you of something we did earlier in this trimester. And that is we graphed absolute value functions using transformations. I want to review that because if we remember how that worked, that will help us as we go through and graph quadratics. So just a reminder, y equals the absolute value of x, the original parent graph, right, it had a vertex at 0. And then it had these straight sides, like each side was linear. Okay. And then we talked about how do we shift it left or right or up or down, or stretch it, compress it, reflect it. We did all those things. So if you look at this first example, it's y equals the absolute value of x plus 4. So just a quick reminder, if you add or subtract on the inside, it moves the graph right or left, but it always goes the opposite direction. So the plus 4 actually moves your graph to the left 4. So now my vertex, instead of being at 0, 0 like it is up there, now it's at negative 4, 0. There's nothing on the outside, so it's not moving up or down, and there's no stretch or compression. So we draw our points. And that's what that graph looks like, right? We get that graph just using transformations. Here's another one. I want you to see, let's see how well you remember it. I'm going to change it just a little bit. I have y equals a negative absolute value of x plus 3 plus 2. So take this function, pause the video, and see if you remember how to graph this using transformations, and then I'll go through it with you. Okay, so the inside number, right, the x plus 3 in there, that moves it right or left. So I know I'm going left 3. The outside function moves it up or down. So I've got to go left 3 and up 2. That's where the vertex of my absolute value graph is. Okay, then I've got that negative in front. That means it's going to reflect it. So instead of opening up, it's going to open down. So I go over 1, down 1, over 1, down 1. That's what that new graph would look like. Just as a review too, let's find the domain and range really quick. So domain is the x values. So you're looking how far left and right that graph goes. And it goes forever. So we say the domain is all real numbers. Or if you use interval notation, you say it goes from negative infinity to infinity. The range is the up and the down. So you're pitching how far up or down the graph goes. Well, the graph starts right up here, right? Starts right there and then goes down. So there's two ways to write that. You could write that as being y is less than or equal to 2. Or the other way to do it is you start from the bottom and go up. You say it goes from negative infinity to positive 2. That's a quick reminder on domain and range. So hopefully that makes sense. Let's do one last problem. Let's do this one right here. Oh, look, it's already drawn for us, so we'll just talk about it. So this one has that 2 out in front, right? It's 2 times the absolute value of x plus 1. So start by finding the vertex. The plus 1 moves it up 1. That's why my vertex is right there. And then that 2 in front is the scalar multiple. Or sorry, it stretches the graph by a multiple of 2, is the way I should have said that. So all that happens, normally in this graph, I'd go over 1, up 1. Now I'm going to go over 1, up 2. And then I could go over 2. Normally I'd go up 2, but I'm going to go over 2, up 4. All of the y coordinates are multiplied by 2. What that does, so if you just a quick reminder, if you think of a stretch, what that really means is it's making it a vertical stretch. It's making the graph steeper. So that's what the vertical stretch. If you do a vertical shrink, it makes the graph less steep. So hopefully that's a good reminder for you. Again, the reason why I wanted to review that is because it's got a connection to what we're going to be talking about today. Okay, so what we're actually talking about today is quadratic functions. So this is a quadratic function. The reason why it's a quadratic function, if you remember when we talked about quadratics in the last unit, we said if your highest power is 2, that makes a polynomial quadratic. So this is actually a polynomial function, but specifically it's the type of polynomial function is a quadratic. So anytime you look at a function and you look at it and the highest power is degree 2, we know that it's quadratic. So we want to find out what that looks like. We're just going to make a table to start with. So go ahead and make an XY table. And let's just plug some numbers in. Let's do both some negative and positive numbers. So let's go from like 0 to positive 3. Plug those in there. We'll get some points and see if we can figure out what this function looks like. So if I plug in negative 3, I'll put it up here. I get y equals negative 3 squared. We'll see if I square negative 3, that's negative 3 times negative 3. That's a positive 9. If I plug in negative 2 up here, same thing, just a 2 there. That'd be positive 4. If I plug in negative 1, it's positive 1. 0 squared 0. 1 squared's 1. 2 squared's 4. 3 squared's 9. So now I have a set of points. Let's go ahead and put those points on the graph. So negative 3, 9. Mine only goes up to 8. I'm just going to estimate where 9 would be. Negative 2, 4. Negative 1, 1. 0, 0. 1, 1. 2, 4. And 3, 9. Okay, so we get those points on the graph. This happens to be what we call a smooth curve. So unlike the absolute value that had that sharp turn, this one doesn't have any sharp turns. So go ahead and connect the points, draw the rest of the graph, but make it a smooth curve. So no sharp turns. So it ends up looking something like that. Hey, what I want you to do real quick is pause the video. And I want you to write down 3 or 4 characteristics of this graph. Like what makes this graph different from others. So go ahead and pause the video, do that, and then we'll come back and I'll talk about a few things that I observed. So hopefully something you recognized is that this does have, it's symmetric, it has symmetry, right? If I draw that line down the middle of the graph, right, that it reflects perfectly about that line. There's actually a name for that. So that is referred to as the axis of symmetry. Sometimes you'll hear it called the line of symmetry. Hey, by the way, on your assignment, you're going to be asked to write the equation of the axis of symmetry. Well, it's a vertical line always. And so that equation would just be x. And if you remember how you write the equation of a vertical line, it's always x equals whatever your x-intercept is. So that crosses the x-axis at 0. Okay, so as an axis of symmetry at x equals 0. Other important things, just like the absolute value function, it has a vertex. Okay, so it's got the vertex as the center of the graph there. That's when it changes directions. It changes from decreasing to increasing. So it's symmetric about that axis of symmetry. It has a vertex. Domain and range. The domain is all real numbers, and the range is y is greater than or equal to 0. You notice that the graph starts at 0, it's always above. Let's see, anything else? I already mentioned this, but somewhere on there you got to have, it's a smooth curve. So there's no sharp turns. One thing that's kind of interesting, this was mentioned actually in class today, is someone said, it doesn't have a constant slope. So the slope, I'm going to write this down, the slope is always changing. Okay, so let's go ahead and what this is, write this down, label this above here. This is called the parent graph. Just like with the absolute value, this is the main graph. So if my function y equals x squared, this is what the graph looks like. What we're going to do next is we're going to do transformations with it, just like the absolute value function. And it turns out that all functions follow the same rules when you're doing transformations. So this follows the same rules as the absolute value. So if I come down here, here's a couple of functions. I have y equals x squared minus 1 and y equals x squared plus 4. And we want to graph these using transformations. So if you think about what we did with the absolute value graphs, y equals the absolute value of x minus 1, or y equals the absolute value of x plus 4, right? If I come back up here with this one, we know that when you subtracted 1 on the outside, it moved the graph down. Well, this is exactly the same then. You're subtracting 1 on the outside, it's going to move the graph down. The only difference is, instead of being an absolute value graph, that V shape is going to be a quadratic graph, which is, oh, I forgot to label this, I'm sorry. This shape of graph actually has a name. Go back up to your notes there. They're called parabolas. So this shape that a quadratic graph we call, it's kind of like that U shape, but it's always curving up. We call those parabolas. So the only difference is, right, on this one is instead of being an absolute value shape, it's going to be a parabola. So I start out the same. I know my vertex is moved down 1 because of the -1. And then from there, I just draw the shape I had up above that parent graph. I go over 1, up 1 on either side. By the way, I think it's helpful if you draw that axis of symmetry. Whoops. Right down the middle there. If I go over 2, 2 squared is 4. So from the vertex, I'm going to go over 2 and up 4. Oops, sorry. Up 4. And then over 2 and up 4. So it's got that same shape. It's just moved down 1. All right, so if we compare that graph, let's see if I can get them on the same screen. Well, that's kind of small. But if you compare those two graphs, right, this graph and this graph are the same, it's just shifted down 1. That's the only difference. So just like with the absolute value graphs, adding or subtracting on the outside is going to move it up or down. So really quick, you don't have to graph this. Take just a second in your head here. Think about what the +4 is going to do to the graph. So if you said moved up 4, that's what it does. So it takes that same parent graph whose vertex is normally a 0, 0, and now it's moved up 4. Everything else stays the same. So from the vertex, I go over 1, up 1, and over 2. 2 squared is 4, so over 2, up 4. And then if I go across the line of symmetry, there's going to be points over here. So that graph ends up looking like that. So again, if we make that connection with what we already learned about absolute values, that makes these pretty easy to do. Okay, so let's look at this next transformation. So again, my original parent graph is y equals x squared. And it's the square that we talked about, right? It's the square that makes it a quadratic. And that graph, we know what the parent graph, I'm going to draw it on here real quick. We know that over 1, up 1, over 2, up 4, right? 2 squared is 4. And it looks something like this, coming down. Okay, that's the y equals x squared right there. So the question is, what happens when I do y equals x minus 3 squared? Well, remember what we talked about with the absolute values. If I have this, if I minus the 3 on the inside, we go the opposite direction and it moves it horizontally, so that's going to move it to the right 3. So if I come down here, this does exactly the same thing. The minus 3 is inside of the square. The square is what makes it a parabola. So if it's inside of the square, it's going to move it to the right 3. So my new graph, I'll do it in blue over here. I take the vertex, I shift it to the right 3, and that's the only transformation. So from there I go over 1, up 1, 1 squared is 1, over 2, 2 squared is 4, so up 4. Okay. And there's my new graph. Everything's exactly the same. Nothing's changed except for, oops, curving up like this, except for it's shifted to the right 3. So what do you think is going to happen with that one? Y equals x plus 1 squared. You don't have to graph it, but take just a second and think about what you think will happen. So the plus 1's on the inside. It's going to shift the graph to the left 1. So shift it to the left 1. All the other points stay the same. So the graph should look just like the original parent graph, the black one there. It's just shifted left 1. The other transformations we talked about, the absolute values, are when you multiply by something. So I can multiply, this one is y equals 1/2 x squared, 1/2, which means 1/2 times x squared. This is y equals 2 times x squared, and this is y equals a negative x squared. Let's really quick look at these three and figure out what happens here. So if you start with that first one, y is equal to let's actually do this one first, y equals 2x squared. So if you remember with the absolute value graph, that stretched it. It made it steeper. So I'm not adding or subtracting on the inside or the outside, so my vertex is not moving. It's going to stay the same. But what is going to change is how steep the graph is. That 2 does what we call a vertical stretch. So that's going to take the graph, and normally I go over 1, up 1. But because I'm timesing by 2, now I go over 1, and I times the vertical distance by 2. So I go over 1, up 2. There's going to be another point over there. And then next, the graph normally goes over 2, and 2 squared is 4, and up 4. But now I'm timesing it by 2. So I'm going to go over 2. And instead of going up 4, I'm going to go up 8, which put me all the way up there somewhere. So what it's doing is just making the graph a lot steeper. When you make the graph steeper like that, we call that a vertical stretch. Okay, let's do this one. We'll do a different color. Y equals a half x squared. So similar to that one, this also affects it vertically. The difference is if the number is less than 1, then it does a compression instead of a stretch. Okay, so what I mean by that is the vertex is still at 0, 0. Still in that same spot. But now I'm going to go over 1. Normally it goes up 1. But now I'm timesing that by a half. And so now I'm going to go over 1 and up a half. On that side, over 1, up a half on that side. Okay, normally if I go over 2, it goes up 4. Well, this one now I'm going to go over 2. And instead of going up 4, half of 4 is 2. So I'm just cutting those vertical distances in half. So what it does is makes it open out a lot, still curving up, but it's just a lot wider. It's less steep. It's not going up as fast. Okay, so it ends up looking something like that. Okay, the last thing is a reflection. So if you look at this last one, y equals a negative x squared. If you remember when we put that in front of the absolute value, it reflects it down. Let's do this one blue. So the vertex is still at 0, 0, but the negative is going to make it go down. So I go over 1. There's no stretch or compression, so I just go over 1, down 1, over 2. 2 squared is 4, down 4, 1 over here. So it's the shape of the original parent graph. It's just reflected down instead of reflected up. So those are all the different transformations. Now, hopefully, if you remember how to do the absolute value ones, that you can make that connection. And that makes these really easy because you follow all the exact same rules. Okay, they're no different. It's just that instead of being that V shape, it's going to be a parabola shape instead. Okay, let's kind of put it all together. So let's take this one right here. It says g of x equals negative 2 times x plus 2 squared plus 3. It says compare the graph to the graph of f of x equals x squared. This is just the parent graph, right? This is the original. It wants us to compare that one to it. So pause the video, take just a second. I want you to make a list of all the different transformations. Like how is this graph different from f of x, from the parent graph right there. So pause the video, write down your list of transformations, and we'll come back and we'll talk about it. Okay, what we should see, right, is the plus 2 on the inside shifts it left 2. The plus 3 shifts it up 3. So here's my original graph, right? Then over 2, up 4. So my original graph looks like this. Now this one, though, we'll do a different color. It's been shifted left 2 and up 3. So now my vertex is right there. The negative 2 does two things. It reflects it down, plus there's a stretch. So normally I go over 1 and down 1. But because I'm timesing by 2, I'm going to go over 1 and down 2. And there'll be another point over here on the other side. My next point is normally I go over 2, right? And then I go up, and normally I go up 4 or down 4. But because I'm timesing by 2, I'm going to go down 8. So over 2 and down 1, 2, 3, 4, 5, 6, 7, 8. Then there's another point over here. So my graph ends up looking something like that. Okay. So all those same transformations we've already done with absolute values. Let's have you, I want you to try this one. So pause the video and graph that, and then come back and I'll draw it with you and we'll compare our answers. Okay, what you should have seen is, right, I'm gonna go left 4 and down 2. That's where the vertex of my parabola is. There's a positive 1/2 in front. Okay, that's gonna be a vertical compression, so it's gonna be less steep. So normally I'd go over 1 and up 1. I'm gonna go over 1 and up 1/2. That's really hard to draw, especially without graph paper, but just do the best that you can. The next one, normally from the vertex, I'd go over 2 and up 4. But because I'm timesing it by 1/2, I do 1/2 of that. So I go over 2 and up 2. And there's a point there. And a point there. So it's got that compression. It should be less steep. Again, that's hard to draw precisely, but that's okay. Just get the general idea. So, right, I went left 4, down 2, and when I times by 1/2, it did the book, I could been calling it a vertical compression. I think the book actually calls it a vertical shrink. It just means it makes it less steep. Okay, I think that's it. The main thing here is knowing the transformations for quadratics and any other function is the same as transformations with absolute values that you've already learned. So if you make that connection, you can do it the same way, which makes it nice. You don't have to learn a new set of rules there. Okay, good luck.